Okay, good evening, friends. So, in the last class, yes, good evening. In the last class, in the last few classes, we have understood semiconductors. We have understood, most importantly, the depletion layer and everything associated with depletion layer. We have understood what happens to the diode when it is forward biased, what happens to diode when it is reverse biased, and we can correlate what is happening inside the diode. And when we carefully examine the depletion layer, what happens, etc. I think these aspects are very clear to you. And we have also used a diode and made something. What is that? We made full wave and half wave rectifiers. Okay?
Yes.
And whilst we did that, we considered the diodes to be ideal in nature. Okay? We considered the diodes to be ideal in nature. In other words, the diodes, see, the diodes, okay, when you say diodes, right, you can use them as a switch, okay, right, or a real diode, okay. So, switch means you use it as ideal diode, and for ideal diode, the characteristic is like this. Ideal diode characteristic is like this. That is diode current ID versus VD is going to be like this. But as far as the real diode is concerned, the characteristics of real diode, as you know, the characteristic of real diode, as you have seen in the last class, it will be like this. Okay, this will be the diode characteristics. I suppose this is clear to you, correct? Yeah. And here the most important thing is, so this region is forward bias region, and this region is reverse bias region. Okay. Now we have discussed at length what is there at this point. Why it happens like that here? Because the depletion layer is still breaking. It's still becoming narrower and narrower, and by this time we say the depletion layer will vanish. 0.7 volts for silicon and 0.3 volts for germanium, and we call this point as the cutting edge. Correct? Okay. Now here you see it in an idealized condition that you see here. This is the real condition, this is the ideal condition. So yesterday when we analyzed the rectifiers, we have considered this model of the diode. But in reality, this is the situation. Okay. Now imagine the half wave rectifier that you saw yesterday. I think, right? The half wave rectifier that you saw yesterday, right? This was the load RL, and I will say that this is the output VO, and here you are feeding VIN. Okay, and VIN, when we are feeding, VIN is of the nature. What is VIN? VIN is VO sin omega t. VO sin omega t. Correct? And for this, so at the input you will have this waveform. Okay, and at the output you will have what type of waveform? You will have waveform like this. Correct, students? Hello?
Yes, sir.
Versus time. This is versus time. Okay, this is VO. So this we said was VO, and this we said minus VO, and here we wrote this as plus VO, and this is 0. I suppose this is clear to you. If you have any questions here, please ask. Please now make sure that you learn everything perfectly, because the questions in the examinations or in the real world, when you are going to do a lot of designing and becoming great engineers, you have to be extremely sensitive. Okay, when you design. So the questions that can be asked in examinations will be very sensitive. So you have to understand all these things in detail. I suppose there is no doubt in this. Correct? So we got these things. We wrote this waveform for what? For ideal diode. Right? We wrote this for ideal diode. Okay? Hello? Are you with me?
Yes, sir. Yes, sir.
Now in your notebook, if you consider this as a real diode, if you consider this as a real diode, Okay, this as a real diode. Write the output waveform for this input waveform. Write in your notebook, all of it. Whatever you write, you preserve. If it is wrong, you put like this and write the right one later on. Okay, but you should learn like this. So using signs, you write the waveform of the output considering real. Have you written? Hello.
Yes, sir.
Just get it, man. I'm not trying to ask you to draw like a graph sheet and all the things.
Yes, sir.
Right. So now see, the input voltage waveform will be like this. Okay? This is plus VO and this is minus VO. Now for a real diode, you see, now understand one thing. Now here you see, where VO is much larger than V cut in, or V cut in is the symbol for V cut in is V alpha. Okay, right. So I will say now VO is very large than V cut in. Okay, say VO is something like around 5 volts, 10 volts. Then you see, if you say 0.7 volts is insignificant, if you say 0.7 volts is insignificant, and for all practical purpose you will take the diode as what? A ideal diode, then the output waveform for the same circuit would be like this. Agreed? Hello?
Wonder, sir, that waveform till it reaches the cutting voltage.
See, you didn't listen to me. If you consider the diode to be ideal, then this output waveform will be like this. That's what I said.
Yes.
Then you should listen. You are getting into a bad habit. When I am teaching something, because you have learned something in the college, you are presuming, sir, fatafat sikao sir, mujhe malum hai. See, don't do like that. I know what is taught in your college and how much you have understood. You would have missed many sensitive things, and that is going to cost you in your examinations. So better be careful. And when you design in the future, okay, if you design something and some mistake you have made, the whole circuit will collapse. Okay, so now this green line indicates U. Now if you consider the diode to be real, so definitely you are not going to get this waveform. Correct? Why? Because now you see, now what happens? Here say this point is 0.7 volts. This point is 0.7 volts. Okay? So till this, this point is 0.7 volts. Assume this point is 0.7 volts. So till it reaches 0.7 volts, the output of the diode will not be like this. Understand? The output of the diode will be like this. Okay? And there afterwards, if you consider the diode is forward bias, it is forward bias, then you will get the waveform like this. Again, it would be like this. Did you see the yellow line here? Hello? So this is how the output is going to be if you consider the diode to be real diode. Got it?
Yes, sir.
Did you all get it now clearly? That is what I want to emphasize. That's what. So if you say now I am going to neglect it depending upon the numerical, then you can consider this green waveform. That is for the ideal. But for real diode, this is how it is going to be. Right? Then another notable thing is, you have written rectifiers. You see here, VO should be greater than V cut in. Supposing VO is less than or equal to V cutting. Okay, then what happens? The output waveform is not going to be like this. Okay, so therefore, for very, very small voltages, that is VO if it is very, very small compared to V0, okay, compared to that very small or slightly bigger than V0, then you will not get the waveform like this. Is it clear?
Yes, sir.
So this is something that I wanted to tell you. See, this is the way you have to learn. First from ideal condition, then you have to move on to the real condition. The structure of learning science is structured like this. So I am taking you into the real world. Okay, this is point number 1. Now, if you yesterday you see the concept of resistance, correct? Resistance. So what is electrical resistance? Come on, tell me, what is electrical resistance?
The resistance offered to the flow of charge carriers is known as electric.
Yes, opposition to the flow of electric current through it is called resistance. Correct?
Yes.
Now you have to be very careful here, because now you are learning things very deeply. See, now you see here you have heard somewhere in some context, you have heard about current source. I suppose you remember current source. Okay, current source means we have used this symbol. I remember we have taught me electrical this one. This is current source. Now current source is energy source, and this is going to give you constant current. Okay, supposing you keep a load resistance RL here. Whatever be the value of RL, this current will be I only. Yes, this voltage will change. This voltage will change. What will be the voltage? Voltage will be equal to I into RL. But the current will not change if the resistance changes. On the other hand, if you have this is called as what? Constant voltage source. Okay, now here if you connect RL, okay, then here you see the output voltage is fixed. So this is Vin, the output voltage is also V. But this current now, if you vary IL, current will vary. Here current is equal to what? Current is equal to Vin by R. So this is constant voltage source, this is constant current source. Got it?
Yes.
So therefore now here you see whenever you are talking about resistance, whenever you are going to talk about resistance, okay, whenever you are going to talk about resistance, you have to now understand something, that there is a device. You are going to vary the voltage across the device by some means, and you are going to measure corresponding change in the current. Now, a ratio of the change in the voltage to the corresponding change in the current. This is what we call it as the resistance of this device. Got it? And if this value, if this R is constant over a number of over a particular range, so in that range we can say this device is behaving like a ohmic device. Got it? And now from mathematical point of view and geometrical point of view, if you see what is this delta V by delta I, it will represent the slope of the curve. It will represent the slope of the curve. Okay. Now supposing this is voltage versus current, and you have a line like this. What is the slope of this line? The slope of this line is tan theta. Or if you take this, what is this? This is delta V. What is this? This is delta I. So delta V by delta I, what is it? Tan theta. Tan theta is the slope of this line, that is equal to the resistance of this device, which is given to this characteristics. Clear? Hey, come on. If you don't understand, you say, or you tell me to wait, because I have to cover a lot of ground. Lot of such things I have to teach. So you have to keep your mic unmuted and keep saying yes sir, no sir, please wait sir, okay sir, whatever it is. Right. Now, this is what happens. But supposing the characteristic is like this, right? Supposing the characteristic is like this, then you see the slope of this line is the slope of this characteristics V versus I. Okay, the slope of this is different here, different here, different here, different here. That means the resistor is not constant. Delta V by delta I is not constant at all the points. So it is this resistance. So resistance denoted by small letter, indicating that the resistance is not constant. It depends upon where you are measuring the resistance. See, delta V by delta I, if you measure here, then delta V by delta I at this point is so and so. So at this point the resistance is R. Did you get it?
The graph should be I only by axis and V on axis.
See, again, something is wrong with you. Okay, yaar, why you, see, I am writing a graph V versus I. What is your problem? Why you want to relate it to this? I am writing one general graph and explaining some concept. Why are you bothered about that? I am trying to teach you some concept, then you want to learn something ahead. You only concentrate and tell me whether you understood this. Clear?
Yes.
You understood this? Hello?
Yes.
Please be with me. I have to make sure that you understand the concepts properly. Then we will use the concepts in these circuits. Correct? Okay. Now, here as far as the diode is concerned, we are writing it like what? We are writing ID versus VD. VD is the voltage across this one. Okay. ID versus VD, we have got the graph like this. Okay. So now you can see that for this range of values, the resistance is not constant. Correct?
Yes.
Before the diode becomes on. Now, this range, this is also non-linear. But for all practical purpose, you can take this range to be linear. So here, if I make this, okay, if I am making this, what is this now? What is this? This is delta I. And what is this? This is delta V. Hello. And what is this? This is 1 upon R. Correct? Hello?
Yes.
Will you keep your mic unmuted and speak properly? Or you want me to keep on, I am getting distracted. Come on, keep your mic unmuted. You answer quickly. Or else you tell me to wait. So, and since we are measuring the resistance in the forward region, we are going to call it as R. So 1 upon RF is delta I by delta. Correct?
Yes.
So from this point to this point, you will say that the forward resistance is constant. And what you are going to measure is this. Clear?
Yes, sir.
Okay, now coming to another point. So this voltage, call it as cut-in voltage. This voltage I call it as cut-in voltage. Okay. Now that I have got this circuit. I hope you can see this circuit. Once again, I want to draw that circuit. It's a diode with RF. Diode with RF. Okay. Now I am giving V in here and I am getting V over here. Okay, I think you are familiar with this description. Now, as far as the circuit is concerned, remember, as far as the circuit is concerned, that is, I will have to draw the circuit. So, how will I draw the circuit? How will I draw the circuit? See here. This is V in this point. Okay. Then this diode, you see here, diode. As far as the diode is concerned. Okay. So, when the diode is on, that is when the diode is conducting, it has to overcome what? The cut-in voltage. Correct? So that cut-in voltage, I will show it like this. V cut-in. Okay? And then the diode resistance, I will show like this. This is RF. Got it? That is, I am modeling this diode in terms of the circuit elements. And then I am going to write it as R. Okay. So now you see what is the current that is flowing here. The diode current ID will be equal to V minus V cutoff. It would be equal V in minus V cutoff divided by RF plus RF. Got it?
Yes.
Hello, everybody there? See, these are the, you understand, students, you are all used to what you know. You give a numerical problem, you solve, sir, we understand, sir. I have, then that means now I have to solve 100 numericals to explain something. That is not the way to learn. What I am trying to tell you, see, whatever I am teaching, it is linked to your future as well as to the numericals that you are going to solve. So if you understand this, you can solve many numericals. If you solve one numerical, you will understand something related to that numerical. These are all in general. Correct? B in minus B. This one? Yes, please tell me.
Sir, that cutting voltage, sir, it is the voltage at which the depletion region will end, sir. Contact. So after the voltage has increased, that cutting voltage, sir, still why there is drop because
that's a good question. That's a good question. See, this question is really appreciated. Well asked. Okay. See, now what you have to see here, what you have to understand here is, now what we have explained to you that the depletion layer will vanish. Okay, these are all the models that we have developed. These are all the models that we have developed. In reality, what happens? See, the Nd and Na atoms, they are still there in the semiconductor.
Yes.
Isn't it? Still they are there in the semiconductor. Okay, the diffusion current is moving like this. Fine. But at the same time, you see that depletion layer is trying to form. That depletion layer is trying to form. It is not that, diffusion current start flowing, I will not form the depletion layer. No. It is doing its best to form the depletion layer. That resistance is there. That is why we are using the concept of potential energy barrier. So potential energy barrier is always there. And what did I tell you? If a hole from P, it has to go to the N side, it should have energy greater than the barrier potential. Correct? So when it has to overcome this potential energy barrier, okay, it does consume some energy.
But that barrier, sir,
Tell me, correct, tell me.
We have it has reduced, correct?
See, that is very good. Now you see, now things are really opening up. It has reduced, that is how we have explained. But now you see the other part of the explanation. Assume that the depletion layer is still there. Okay, assume that the depletion layer is still there. Hello? Now, and a hole has to go from a P side to N side. The depletion layer is still there. Can a hole from P side go to N side, diffuse to N side? It is still possible, provided this hole on the P side has energy greater than the potential energy barrier energy. Correct? I explained this also to you.
Yes.
Okay, so understood. So therefore, see, when you throw a stone up, it will cross this barrier, correct?
Yes.
It will cross this barrier. Above this barrier, when the stone comes, what is the energy of the stone? The energy of the stone will be whatever it starts here, and by the time it comes here, it loses some energy, and with the remaining energy, it is going to come outside. Understood? So therefore, there is energy that is eaten up by this source. That is why we are showing it like this.
The barrier potential will exist.
See, now, still you are having doubt. Okay, you are having doubt. Good. Now, you conduct the real experiment. And see in the laboratory. You will find that the output voltage curve will be like this. What does it show? See, now, according to what you have understood, if the depletion layer has vanished, then we should have got the curve like this only. Why are we getting the curve like this? Because you understand my explanation. You understand my explanation. See, while we are explaining, we create some concept. And we explain. Correct. But you see, we use some words, some diagrams to explain. Right? And we try our best to see, you know, like what is the reality that I have understood. I want that reality to be understood by you. We do our best. But in spite of that, there still remains some deficiency in understanding. Okay, now that deficiency is, now you see, because I told you the depletion layer will go and all, okay. But when I was telling you that the depletion layer will go, did I ever say that the energy of the holes that crossed over from the P region to N region, the energy of the hole did not deplete. The energy of the hole did deplete, correct?
Yes.
I did not say that energy will be the same. But we solved a numerical yesterday, you remember? A hole enters the P with certain velocity, and the potential barrier is 0.5 volts, if you remember yesterday. And what is the velocity with which it comes out? Did we not solve that numerical yesterday? That is one thing, because sir, the numerical you solved, now we understood. Okay, fine. But at the same time, if you conduct an experiment in the laboratory, you will find the output curve to be like this. It will not be like this. In this experiment, now you can dispute what I said, right? But you cannot dispute this reality. So this very clearly shows that the electron or the hole which is crossing the junction is losing some energy.
Then that output voltage is like that thing said. That peak voltage what will be?
Correct. You are a wonderful student. Hinge ಕೇಳಿ ಇನ್ನು ಈಗ ನೋಡಿ ಇಲ್ಲಿ ಬರ್ದಿಲ್ಲ ನೋಡಿಲ್ಲ. Can you not see this?
Yes.
So this difference is weakened. Good boy. See, you should ask questions like this. See, then only you know मैं मेरा काम कर रहा हूँ, आप अपने काम कर रहे हैं. ठीक है? The Almighty, nature, Khuda, you know, whatever you call God, He will be pleased and He will bless both of us. Because we are doing our duty. You are doing your duty as a student, I am doing my duty as a teacher. Sir, here you see both you are involved and I am involved. I am making you to think like this. That is my duty. And you are thinking, that is your duty. Now, I did not have to explain all this. It is not given in your textbook. So, but it is implicit. You are supposed to understand that. But I am making it open. I am igniting all of you. Come on, think. That's my duty. I am doing that. And you are doing your duty. Keep doing it. This is precisely what I want to happen in my class. And that's why I am teaching. This is a pleasure teaching for me. Right. Did you all get it now, students?
Yes.
So this is also called as piecewise linear model of the type. Because what we do in circuitry is, you know, we cannot see now a P type of a semiconductor, N type of semiconductor, metallurgical union, depletion. There's so much of theory for over 3 hours we have learned, 3 to 4 hours. Now every time, you know, we can't use that. So we create a circuit model so that we can easily solve the circuit problems using this model. So we create this model and we write the corresponding equation of it. Did you get it, students?
Yes, sir.
Now, what will be the output voltage? Output voltage will be ID into R. Output voltage will be ID into RL. Okay, this output voltage that will be. Okay, so therefore finally the output voltage will be what? V in minus V cut in. Mr. Murthy, be cool. I am only telling myself. V in minus V cut in divided by RL plus RF. This is current into RL. This is your. Did you get this equation?
Yes, sir.
Now you see, if V cutting is very small compared to V in, means V cutting is very small compared to V in, then approximately you can write it as V. And if RL is very large compared to RF, then you can write it as RF. You can write it as You can write it as what? R into R. So this is cancelled. So V out will be equal to V. That is precisely what we did yesterday. When you are making, when this is insignificant compared to this, and when this is insignificant compared to this, and that is precisely what happens in ideal diode, then you will get V out is equal to V in. So input will be equal to output. Got it?
Yes, sir.
Great. So this model what I have written is when the diode is on. But when the diode is off, that is this part. Okay, then what will be the piecewise model? Anybody can tell me? What will be the piecewise model? Tell me. Real. Ideal oscillator, real oscillator. Okay. दोनों बोलो जी क्या है?
Ideal sir, it will be open circuit, sir.
Excellent.
For ideal sir, there will be a large potential opposite like
पोटेंशियल नहीं, हाँ अभी देखो, ठीक है, आप ठीक तरह से सोचो, मैं आपको you think properly, and if you have not thought properly, I will correct you. That is my job. See now how you have to look at it. How you have to look at it. Here you see, even though the voltage is changing, the change in the current is minimum. That is, if you see this point, change in the voltage is large, but the corresponding change in the current is very, very small. So this is approximately equal. So this one, see now here in this range, delta V by delta I will give rise to what? RR. That is reverse saturation resistance. Correct? Or the resistance in this one. And this is approximate. This value is very, very large. Hello, are you with me?
Yes, sir.
So when the diode is off, then you have got VIN. Okay, you have a diode. You have this RL. Right? Now, when the diode is off, you will represent this diode by this. By what? By RR. Reverse resistance and RR. Okay, now you see, VO will be equal to VIN divided by RR plus RL into R. Okay, hello.
Then R will be very large.
Next thing you have to do, basically write this. Now RR is very large. If RR is very large, then RL. Got it?
Okay.
Then for our practical purpose, you will get V out will be approximately equal to V out RL divided by RL. So what you see is you will get very small output. Okay, very small output. So what I am trying to tell you, here in ideal condition we are writing the output waveform like this. But in the real condition, the output will be got it?
Yes.
A small voltage है, A voltage. Understood?
Yes, sir.
देखो कितनी बढ़िया है. See how nice it is to learn. See, theoretically you see, by understanding something, we are telling that this is what happens. Go to the laboratory and do it. You will get this. And see, if you are able to relate what you have understood theoretically and what is happening practically, that means you have understood. Science triumphs there. Okay, fine. I think I have made all these things clear to you. Hello, shall I proceed?
Yes, sir.
Fatapat, you should tell me yes. If you have doubt, you stop. See, Adil is asking nice questions. Arun asks nice questions. Okay. Abhinav tries to answer. He also asks. But others are simply keeping quiet. God bless you. Now let's contemplate on these circuits. Okay, you can see these circuits. So you can see this circuit here. So what is done here? A voltage source is taken. What is this? This is called rheostat. I think you know this. You have used it in the laboratory. So if this wiper is moved, okay, you can see here that this is taken as common point. So that means now if this wiper is here and if this voltage is V in, then if the wiper is here, the voltage at this point will also be V in. If this wiper is here, the voltage here will be 0. So anywhere in between, you know, the voltage will change. Got it?
Yes, sir.
So you can get whatever voltage you want, whatever no, between the limits V into this. You can get it. You are feeding it to the diode, and then you have connected. What is this? You have connected a voltmeter. Correct? Hello.
Yes, sir.
Voltmeter, and you have connected a ammeter. It is in milliamperes, it is in volts. And then you have got an output resistance RL, which is variable. That is the basic setup. This is the basic setup for what? To get what? To get the forward characteristics of a diode. ID versus VD. So this voltmeter will give you this VD, this current will give you ID. Got it? So here when you conduct this experiment, you will keep RL constant and you will go on varying this voltage. If you vary this voltage, this VD will change, and when you vary this voltage, this VD will change, corresponding ID will change. So you will get all these points. You join the points, you will get this curve. So this is how this experiment, you are going to conduct this experiment in the laboratory and you are going to get this curve. Okay, now the same thing now, you see, you will connect the diode ulta. Right, in the reverse bias, and you will conduct the same experiment, then you will get the points and you can plot this. So here you see in the laboratory you will get this point, only up to certain range. They will not allow you to burn the diode in the laboratory. So you will get the diode characteristics like this. Correct? And this is the experimental setup for this. You will not get this point, I am telling you, in the laboratory. You will only get up to this point. Okay, got it?
Sir, like VD is output potential or potential across that diode?
Potential across the diode. VD is potential across the diode. VD stands for the potential across the diode. That is VO. See, this experiment is to get these characteristics.
Okay.
Got it? Now, ideal diode. You see it has a switch. Behave like a switch. For all, RR is approximately equal to 0, infinity, and it will be RF will be equal to 0. So here you see RF is equal to 0, RR is equal to infinity, right? And when it is this one, so V cut is 0 here, and here it is infinity for ideal diode. Everything is clear. Correct?
Yes, sir.
See, because you are going to use diode not only for rectification, for your Boolean algebra also you are going to use it. You got to solve many interesting problems considering diode as a switch, considering diode as a rectifier, and Zener diode, and then real diode, etc. So many interesting questions you are going to answer. So just be prepared for all that and learn theory. If you learn correctly, then in the examination, any situation given, you can analyze the situation and write appropriate answer. I am telling you students, even though you solve 1000 problems, in the examination you are going to get 1001th problem which you have not solved. And don't think that 1001th problem will be similar to one of the problems that I have solved. So I am going to do. No. You cannot remember 1000 problems and you cannot correlate with the examination condition because you have never faced the real examination condition. But that is all wrong method. Right method is you learn science thoroughly, let them ask 1001 or 1002 question. Using science you analyze, you will definitely be able to answer. Yes, by solving 1000 problems, you will practice speed, accuracy, and yes, the knowledge base will also increase. But what you gain by that is something added to learning theory properly, you will be able to do very well in the examination. Okay, now, okay, shall I proceed?
Yes, sir.
Thank you. Now that yesterday we have studied rectifiers. I suppose we studied rectifiers yesterday. I hope you remember. Now rectifier. I showed you yesterday half wave rectifier, full wave rectifier. In full wave you have got center tap rectifier and bridge rectifier. We have studied all this. Now you see. Now what is it? So in the book they have given that alternating current, alternating voltage is converted into DC voltage. Now DC voltage means, see now what is written, what you have to understand from the definition given in the book is, this they call it as alternating current. Okay, this they call it as alternating current, or sorry, alternating voltage. Okay, this is what they meant. What definition I have given is, consider a sinusoidal voltage waveform of zero average value. That's what I meant. It is converted into another waveform whose average value is non-zero. Correct? Do you remember yesterday's definition? So if you pass this waveform through a half wave rectifier, then you are going to get what? You are going to get this waveform. Correct? Half wave. Okay. Now we calculated the, see, if you take the average of this signal, that is integration sine omega t. See, integration V naught sine omega t, d omega t, 1 over 2 pi, if you do this, okay, 0 to 2 pi. So, if you, this is nothing but the area under the curve. So, the area under this curve is positive, the area under this curve is negative. So, this will simply be equal to 0. So, the average value is 0, correct, of the signal. On the other hand, if you integrate this signal from this point to this point, 2 pi, okay, so what happens to due to this integration? This also you write it like this, 1 over 2 pi, 0 to 2 pi, V naught sine of omega t, d omega t, same thing. But you split this integration, 1 by 2 pi common, 0 to pi sine V naught sine omega t, d omega t, plus pi to 2 pi. Okay, pi to 2 pi V naught sine omega t, d omega. Got it? Now you know that for this range, what, pi to 2 pi, it is 0. So this data will become 0. So you just have to integrate this and divide by 2 pi. Yesterday when we did this, we got it as what? We got it as what? V naught divided by, hello, what did we get here?
V naught by pi. No sir, V naught by pi.
Got it? We got it as V naught by pi. Remember, what is this V naught by pi? It is the value. And where will you get this value? See, if this is V naught, you divide V naught by pi, approximately 1/3. So, this point, what is this? This dotted line I am drawing here. Okay, what is the dotted line I am drawing there? This is what is this? This is the V average value. Got it? This is one part of the story, right? Okay. If you have questions, you ask her. Don't sit quiet there. If you don't understand any point, I will be very, very happy to explain. I enjoy, students asking questions, that are very interesting questions, correct questions. Not some faltu question, to prove your point and I will answer to prove my point. Then both of us are going to waste our life. We should not do that. We are not here to prove any point today. We are just here to enjoy learning science, including me. Right. Okay, friends. So now here, at the same time, so you are getting this waveform, right? This waveform. One of the abstractions is V average. That is, it is a statistical average. V average is a statistical average. Okay. There is one more you can take. What is that? So what we have got here is, we have just got here V average. V average is V naught by pi. Now you can also get the RMS value of this. V RMS. Right? So again, what will be V RMS here? root means the value. So same thing. Integration 0 to 2 pi. Okay. V naught sine omega t square root of mean of squares. Okay, this gives you VRS. Hello students, I have already done this when I taught you electric current. Hello. I am sure you would have forgotten. So what is V naught sine omega t? So you will take V naught square outside here and 2 pi will be there, and integration of sine square omega t, you are going to write it as 1 minus cos square omega t. I suppose you remember that, right? Hello.
Yes, yes.
You are going to write it 1 minus cos square omega t, and cos 2 omega t will give you 1 minus 2 cos square omega t. So therefore cos square omega t will be what? Will be what? 1 minus cos 2 omega t divided by 2. Got it? Hello. Hello. By doing all that integration and all, and then dividing by this one, you are going to end up with V naught by 2. If I do that and see, you will get this. What is this? This is the VRMS value. This is the VRMS value of this thing. Correct? Now you understand these two statistical average. What is RMS value? That is for full wave.
Yes.
That is for full wave. This is for half wave. Am I right, Arun? Arun, Abhinav. Aryan, for some reason, he has gone into shell. I don't know what is wrong. He makes the thing on and he vanishes. Yesterday I was shouting his name, he was not responding. Something is wrong with him. What, Aryan?
Yes, sir.
What, yes, sir? You are not answering these days. And then you are not present in the class also. Yesterday I shouted again. You are not to be there. God knows. Okay, anyways. VRMS is this. Now, where will you use this statistical average V average and where will you use this VRMS? Where will you use these two? See,
VRMS will be in a situation.
Continue.
When there will be components in the circuit, we should use VRMS.
Pardon? Once again.
When there are when we are using the AC circuit, we should use VRMS.
No, that's not a thing. Anybody else? Okay, now understand this very carefully. See, you are getting this output, correct? This waveform you are getting. Hello?
Yes, sir.
You are getting this waveform. That is the output. Reality ये दिया. इसमें से from this I want to do something. From this output I want to do something. Then when I want to do something, I need to know its value. This is the output waveform. Then using this I want to do something, and to do something I should know what is that value of this I should consider. Okay, now listen here very carefully. So now here you see students, I have this rectifier. Okay, I have this rectifier here with me, RL, and here I am giving V in here. V is what? V naught sine omega t. I am here. I am getting here. Now I want to charge a capacitor. Hello.
Yes, sir.
See, now if I connect a capacitor directly to Vin, what will be the charge stored in the capacitor? It will be 0, because whatever charge enters the capacitor for the positive cycle will be removed during the negative cycle. Got it?
Yes.
On the other hand, when the waveform here is like this, then what will be there in this capacitor? See, now here, as far as charging the capacitor is concerned, the current should flow only in one direction. Hello, the current should flow only in one direction? No. See here the current is flowing like this, therefore no charge will be sustained. Because the average of the waveform that you are going to feed is 0. But here the average of this is not 0. Therefore students, now you understand this very carefully. If you have this sort of a circuit, then you will consider the average value of the circuit, average value of this waveform, and then you will do some calculation, because you are interested in the average value. What is this average value? So depending upon this average value, I am going to charge the capacitor. Got it?
Sir, but when there is continuously changing potential, sir, won't that charge won't be fixed, no?
It will not be fixed. It will not be fixed.
So then why everything? What is it?
That is. Okay, now ask question. You will get the idea. You will get the idea. Don't worry. Huh? See, now I have got this. Okay, I'll take a clean board for you and solve it. So here I am going to feed V0 sin omega t. So here the waveform is going to be like this. And here, if I connect a capacitor, okay, so here you see, what is the waveform I am going to get at this point? Of course, this is the common point. What is the waveform I am going to get here? The waveform I am going to get here. The waveform I am going to get here. Now listen very carefully. Supposing the capacitor is not there, what is the waveform that you are going to get here? Yes, you will get this thing. Correct?
Yes.
Right. This is the waveform we are going to get. Now, if I connect a capacitor, now what will happen? See now, aram se this voltage will rise. So this voltage, this point will rise. So the voltage across the capacitor will rise. Correct? Up to this point. Hello?
Yes.
Then what happens? That diode was on. Now after reaching this point, see this capacitor is now charged to plus V0. Correct? And now this voltage has started becoming negative. That means this diode will become off. Correct? Hello?
Yes.
So formally, whatever current was flowing here, some current was flowing here, some current was flowing here. So both the voltages were rising like this. But now, once it has reached the peak, now this voltage now becomes negative, isn't it? See, now the input voltage here, this voltage was rising. Okay, so the corresponding, so this is V in voltage and this is V out voltage. So V out voltage was also rising. Hello, are you with me? This was rising, this was rising. Now this input voltage will start falling. But here this voltage is now VO, but this voltage now has become less than VO. So the diode will become off. The diode will become off at this point. From this point to this point, the diode is on. Now here the diode becomes off. Why it becomes off? Because this is more positive than this. Correct?
Yes.
But so now whatever is the charge in the capacitor, it starts discharging through this resistor. So the capacitor voltage now starts reducing. Correct? Now starts reducing the capacitor voltage. So VO is what? VO is nothing but the voltage across the capacitor. Correct? And it is nothing but the voltage across the distance RL. All three are same. And now once again here the voltage is reduced. Now again you see the input voltage, of course, is behaving like this. The input voltage is behaving like this. This is the input voltage. Now, what happens? See, the capacitor voltage is now decreasing because it is discharging. Now, when the input voltage is having this value and the capacitor voltage is also having same value, now the moment the input voltage becomes slightly larger than this, once again this voltage will start rising. So, sorry, this was going up like this. So here the voltage started rising. So from here onwards, once again the capacitor voltage will rise. The capacitor voltage will rise. Once again become like this. So this is the waveform that you are going to get across the capacitor. Got it? Good. Now again you see this average value of this is this. It is not perfectly DC.
Okay.
But it is चलता है, हमारा काम चलता है. क्योंकि हमारा काम क्यों चलता है? क्योंकि say for example your mobile charger from the mobile charger you are going to actually, if you see the waveform coming out of the mobile charger will be like this. Charge तो हुआ ना, हमारा काम हो गया. ये charge current if this is steady DC then only it will charge. No, ऐसा हुआ तभी हो चलता है. See, now we want a very smooth road to travel. चलेगा. थोड़ा ऐसा हुआ तो क्या प्रॉब्लम है क्या? चल सकते हैं ना. Unless you are महाराजा and महारानी चल सकते हैं. हमारे हुबली में तो पूरा रोड घंटा पट्टा रहता है, फिर भी हम चलते रहते हैं. चलेगा. So that is where you will use this average quantity. So you will find the average value of this. So therefore, if you use a capacitor, then the average value of the output will increase. If you don't use a capacitor, the average value will be less. That is the significance. Correct? Now, then highest is ask.
No, sir. Good. Yes, sir.
Good. Okay. Now, when will you use the RMS? Yes, we want to know what is the power at the output. We want to know what is the power at the output. That time we will use VRMS. Got it? We just want to know what is the power of the output signal, what is the power of the input, what is the power of the output. So VRMS, okay, V in का RMS value कितना होता है? V naught by root for half wave. Okay, and V out of RMS will be what? V naught by 2 for half wave rectifier. For full wave rectifier, this will be V naught by root 2 for full wave rectifier. कुछ भी नुकसान नहीं हुआ पावर के बारे में. Unless diode has consumed power, all the power at the input is available at the output. Only thing is the waveform at the output for full wave will be like this. It will not be like this. But as far as we are concerned, either current goes like this or like this. If the resistor is consuming the power, so it is V naught by root 2. Done? Got it?
Yes, sir.
They'll ask. That's it. So we are missing this. Okay. Now, as far as the performance of the rectifier is concerned, performance, we need to have some performance parameters. So those performance parameters is what we study. I hope you can read all this. What is written here? You can read the performance parameters. So we define something called as form factor. Form factor means IRMS by IDC or ERMS by EDC. Right? So what is ERMS for half wave rectifier? ERMS for half wave rectifier is what? V naught by 2. And EDC, E means output voltage. EDC will be what? V naught by pi. Hello. So this gives what? Pi by 2. What is pi by 2? This is the form factor. It's a performance parameter. Okay. So the form factor is defined as IRMS by IDC or ERMS by this one. For full wave rectifier, the form factor is pi by 2 root 2. For half wave rectifier, it is pi by 2. I think you can do that. Form factor for full wave rectifier will be V naught by root 2 divided by V naught 2 V naught by pi. The average value of full wave will be V naught by pi. V naught cancels. So it will get pi by 2. So the form factor for full wave and half wave is U. Did you understand that?
Okay, yes.
See, it is a performance. I want to understand, you will understand the meaning of this. No, you will understand slowly. What is the meaning of form factor of this? Means it has its own significance. You will understand that slowly. Now, yes. Pardon?
Which one is good? Like?
You will understand. Everything will have advantage and disadvantage in life.
Okay.
Life is, see, now reality is like this. We are making some diodes, we are making some circuits. So now you will have advantage and disadvantage of everything. So, but to compare, we need some criteria. So there is something that we are going to compare, and for that we are creating the performance parameters. See, for example, you are healthy. How do I know you are healthy? So if you see your blood report, there are so many parameters. So the doctors will see this report, hemoglobin, this, and then looking at those performance parameters, they will tell you are healthy or you are not healthy. Correct? हम इंजीनियर लोग भी ऐसे करते हैं, हम कुछ पैरामीटर्स क्रिएट करते हैं और उसको लगा के हम बोलते हैं ये अच्छा है, ये बुरा है, ये ठीक है, ये नॉट ठीक है, डिसएडवांटेज दिस। मालूम हुआ? ये फॉर्म फैक्टर भी ऐसा ही कुछ है। ठीक है, आपको समझ में आ जाएगा। थोड़ा सफर रखो, क्या बोलते हैं उसको, ओके। नाउ देयर इज समथिंग कॉल्ड एज रिपल एंड रिपल फैक्टर। ओके, हेलो, आर यू विथ मी? आराम से, be with me, don't worry. See, all this is necessary, man. At this time, they have included the semiconductors and communication in advanced also. Till now, it was only in mains and NEET. Now they have included these chapters in advanced also. That means you have to learn them in more depth. Okay, and this depth, what I am teaching is nothing. To be very frank, still more deeply I have to teach. But time is so less. I am trying to teach as much as possible so that I give you the fundamentals properly. Yeah. Now, you see, other day Mr. Abhinav was asking, sir, output you said DC. Okay, see, now for half wave rectifier, you have the output like this. Sorry, for half wave rectifier, you have the output like this. Correct? So I told the average value is. So this is actually given by something pulsating DC. This is also called as pulsating DC. Or you see here, there is an average value for the signal. Pardon? Pardon?
Pulsating, sir. Why is it called pulsating DC, sir? Because see, above this average value, you have got this waveform. It is appearing like a pulse, one after the other. That's why it is called pulsating DC. Some name is given to this. That's it. Now here you see, actually, frankly speaking, we wanted an output which is like this. Ideally speaking, we wanted DC output. But we are not doing it. There will be some ripples over this. You saw ripple means what? See, abhi pani hai. If you go to Udkal Lake early morning, it will be plain. If you drop a pebble, then you will get ripples on that. Okay? So these ripples are overriding the average value. Got it? Now, you see, what you have to understand is, what is the ripple content? What is the ripple means? Ripple factor means, what is the ripple content in the output? What is the ripple content in the output? See now. Now, if you see this waveform, okay, and so the average value is this, for this, Vm by this. Now, if you see full wave, okay, so the average value of this is this. See, this average value is what? This average value is what? V naught by pi. What is this value? Average value? 2 V naught by pi. So you can see that the ripple over this value is lesser than the ripple over this value. Okay? Now you will soon learn in higher classes that you are going to get output something like this. Then you see the ripple content is very less. in this. And down further you can make circuits where, you know, it is like this. Then you see, this is almost a DC. So here the ripple content is very less, here it is less, here it is still less, but here it is more. Got it? I push down to low, say, got it or no? Hello? Hello? So,
Yes.
see here, the ripple factor here is less, right? Least, it is less, it is slightly more, it is very much more, got it? So, by looking at the ripple factor, you can now understand the smoothness of the DC, of the output. So, here you see the DC is very smooth, here it is just smooth, here it is okay, it is not, it is very, very less, the smoothness is not there, got it? See, smooth road, rough road, how do you say? Like this, smooth waveform, smooth DC, not so smooth DC. So, something to compare is this ripple factor, okay? Now, around say, look at these equations, you will understand what is this. Now, try to understand this very carefully. Okay, shall I continue, students? Are you fully alert and aware? Come on, yaar, you have to get up. See, all this I studied in second year and third year engineering. Now you are all going to learn this for second year, that too at much deeper depth than what I studied in engineering, second year, third year. And you are going to face the world's toughest exam. You have to rise to that occasion. You cannot sit here and say, look, I want a very good marks, I want very good rank, I want very good college. You will not simply get it like that, unless you put the right effort. So every day night I am sleeping at 2 o'clock. That is not the donkey work that is necessary. What work is necessary is, in the classroom you should be alert. You should make every attempt to learn. You should cooperate with the teacher. You should try your best to learn. And you should interact with your teacher. That is learning. That is hard work. Okay. Now, you see, you can see this waveform here. Hello? I keep shouting and you don't. College sums ಮಾಡ್ಬಿಡ್ತಾರ that is what is learning ಅಂತ ತಿಳ್ಕೊಂಡಿರಿ ಮಠ ಹತ್ತಿರ exam and ಮುಂದೆ real life ಒಳಗೂ ಮಠ ಹತ್ತಿರ ಈಗ ನಿಮ್ಗೆ ತಿಳಿಯೋದಿಲ್ಲ. You will not understand because you are going to write your final exam somewhere in April, May and all. You would be out of the college and then whatever happens. You will not correlate to what happened in day-to-day class. Actually, what happens on that examination day depends upon what you do every day during these 2 years. Okay, even one day if you have missed that question comes there, then your ranking goes to dogs. So, what is the waveform that you get here? This is the waveform that you get here, correct?
Yes.
Say yes no louder, everybody.
Yes, sir.
Now, if I connect a capacitor here, right? If I connect, see, I will take connect R. If I connect a capacitor here and connect this, now what is the waveform I am getting here? See, this is point A. This is the voltage at point A. Now this is point B. What will be the voltage waveform at point B?
Sir, it won't exactly still be a straight line, but it will smoothen up.
Don't assume, man. Don't
Because
assume.
the capacitance will
Don't assume. See, all that you have to say is, you see here. Now the current starts flowing. Okay, this voltage is coming here. Now this capacitor gas starts getting charged. This capacitor, because the current will start flowing like this. The current will start flowing like this. Hello, are you repeat? So what this capacitor will do is, it will eat away this, whatever is this voltage. This voltage is, what is this voltage? V average, and this is also, we call it as VDC. So the voltage across this will be VDC. And the voltage that comes out of this will be pure AC. So this waveform that you see is combination of two signals. What is the combination of two signals? The combination of two signals. One signal is
one signal is this, and another signal plus another signal. What is another signal? Another signal will be like this. I'll write it little bit. I'll write. So this waveform is combination of two waveforms. What are the two waveforms? One waveform is this, plus another waveform will be this. Another waveform will be this. This is 0. So you see, understand? See, from this waveform, if I take out the DC, then this waveform will reduce to this. This plus this is equal to this. Correct? So this is pure AC, this is pure DC. So this waveform is pure DC plus pure AC. You are going to get this waveform. Did you get that?
Yes.
Please get it. Okay?
The resultant platform can explain
You try to correlate now. See, if I pass this signal through a capacitor, the capacitor will sustain the DC part and leave the AC part. So at this output, if you keep the oscilloscope, it will show like this. Correct? So this waveform, see, to this waveform if you add DC, तो क्या होता है? ये waveform ऊपर उठता है. This value is DC. Got it? So this is voltage waveform. Voltage waveform divided by RL will give you IDC. See here, IRMS. Go up, man. Go. You can see here, IRMS is equal to root of IAC square plus IDC square. Got it? Root of IAC square plus root IDC square is equal to IRMS. Got it?
So that IAC square.
IAC square means, see, just now I told you, if see, I have told you this is the voltage waveform. That is V output AC waveform. If I divide this by RL, what is RL? This RL. If I divide this by RL, then what will I get? Voltage upon RL will be the current. That will become IAC square. This waveform, if I divide it by RL, then see, this is the voltage across this. This is VAC. VAC divided by RL will give you IAC.
Yes, sir. But we are considering what, sir? What?
Considering what means what?
IAC is not fixed muscle.
It is not fixed there. It is not fixed there. Who told you it is fixed there?
Okay, yes.
See, when I write IAC, when I am writing IAC, okay, I got your point. I got it. IAC means, your point is correct. IAC means what? Good man, good. See, you ask your doubt, aram say properly. Sir, I did not understand what is that IAC. You ask properly, no, why are you hesitating? IAC means RMS value of the AC component. So this is DC component and this is AC component. This is DC component and this is AC component. RMS value of the AC component, I am writing it as IAC. Got it?
Yes.
Good, dear. See, wonderful question you have asked. Why are you hesitating? You are a wonderful boy. You be brave and bold and ask. Don't be afraid of anybody in this world. Is it clear? First thing, those people who start getting frightened, they will do nothing in life. Don't be afraid. We are all born one day. We are all going to die one day. That is for sure. In between this, we have to do some good work. That's all. मुसीबत आता है, जाता है, पैसा आता है, जाता है, कुछ भी होने दो. But we should be brave and bold all the time. Then only we can do things in life. Our dimag will always be working properly. We will always be going in the right direction. The moment you start fearing, then your mind is cluttered and then you do nonsense. So just don't be afraid. Just be fine and ask. Okay, sometimes if I get wild and if I shout, then you say, pray God and say, let God give you
ಗುಡ್ ಚಲೋ ಬುದ್ಧಿ ಕೊಡಲಿ ಅಂತ ಪ್ರಾರ್ಥನೆ ಮಾಡೋದು ಅಷ್ಟೇ. ನಿಂದೇನು ತಪ್ಪಿಲ್ಲ, ನೀ ಡೌಟ್ ಕೇಳಿದ್ರೆ ಹೇಳ್ಕೊಡೋದು ನನ್ನ ಧರ್ಮ. ನಾ ಹೇಳ್ಕೊಡ್ಲಿಲ್ಲ ಅಂದರೆ ದೇವ್ರವ್ನಿಗೆ ಒಳ್ಳೇದು ಮಾಡಲಿ ಅನ್ಬೇಕಷ್ಟೇ. ಬಟ್ ನೆಕ್ಸ್ಟ್ ಟೈಮ್ ಮತ್ತೆ ನೀ ಡೌಟ್ ಕೇಳಬೇಕು, ಬರೋಬ್ಬರಿ ಡೌಟ್ ಕೇಳಬೇಕು. ಆಗುತ್ತೆ ಸುಳ್ಳು ಏನೋ ಡೌಟ್ ಕೇಳ್ಬೇಕಂತ ಕೇಳಿದ್ರೆ ನಾ ಬೈತೇನೆ ಅಷ್ಟೇ. ಹಾಂ, ಈಗ ಹೇಳಿದ ಅಂಡರ್ಸ್ಟುಡ್. IAC means RMS value of the AC component. ठीक है? Okay. हाँ. So therefore the total RMS value is split into two. The root of the RMS value of the AC component plus the DC component. Got it?
Yes, sir.
Huh. Now, ripple factor is defined as what? Ripple factor is the ratio of the RMS component of the output to the DC component of the output. IAC upon IDC. Correct?
Yes, sir.
Yes, sir.
See, these are all asked in your examinations, sir. I am not simply teaching you just because I have to teach. I have gone through your question papers. So learn all these things properly. Right. Ripple factor is IAC upon IDC. The RMS value of the output divided by the DC value of the output. What is IAC upon IDC? So if you go by this, then you will bring this out. Then you will get it as ripple factor is equal to IRMS square upon IDC square minus 1. Okay, now how did you get this? See, here you open the bracket, you will get IRMS square. IRMS square is equal to IAC square plus IDC square. Got it? Hello? Now you pull IDC square this side. So IRMS square minus IDC square is equal to IAC square. So IAC will be IRMS square minus IDC square. Substitute there. Then you will get ripple factor is equal to IRMS. What is this IRMS? IRMS is the IRMS value of this full waveform. Okay? IRMS square of this divided by IDC square minus 1, or IRMS by IDC I already defined as a form factor. So ripple factor is equal to form factor square minus 1. That is why the form factor is being used. Got it?
Yes.
Okay. Now you have defined efficiency in machines. I suppose you remember that. Hello?
Yes, yes.
You have defined efficiency of machine. What is efficiency of a machine in mechanics? What is efficiency of a machine?
Sir, input power ratio of input power supplied to ratio of output useful powers coming out of a machine to the input power supplied.
Good. Ratio of the useful output power to the input power, or ratio of the useful output energy divided by the total input energy. Fine. Now, when you talk about, so for us now, rectifier is a machine. It is going to convert, the purpose of that is to convert AC to DC, correct? So therefore, the efficiency of a rectifier, you can see here, efficiency is a PDC, power of the DC component, divided by PAC, the power of the input. Correct? Output power divided by output DC power divided by input power. Got it? See, now so this is V in, correct? And for a half wave rectifier, this is V out. Got it? Hello? Hello?
Yes, sir.
Now efficiency is useful output power. What is the useful output power here is PDC. And what is the input? P of the input. PDC for the output divided by Pin. What is Pin? Pin is the RMS value of this or the power of the input. PDC is the DC power of the output. Correct? See, we are not, see now if you take now the power of the output, what will be the power of the output here? If you consider this full waveform, that will be what? PO ka RMS value. This is what? P in ka RMS value. But that is not efficiency. We are not interested in this waveform. We are interested in this value. How much is this DC value that you get for this input? Okay, so therefore PDC defines what? The DC value of the power of the DC value of the output divided by power of the input RMS value. Okay?
Yes.
So here, what is PDC? IDC square into RM. What is P input RMS value? I input RMS value. I input RMS value is same as I output RMS value into RF plus RF. Into RF plus RF. That is rectifier efficiency. Okay? Pucho.
The output power, like, why they are considered only DC over
because what is the efficiency of a machine? Useful output power, isn't it now? देखो अगर आप कार में पेट्रोल डालते हो क्या नहीं, वो इनपुट पावर होता है, ठीक है ना? वो जो पेट्रोल डालते हो, why do you put the petrol in the car? So that your car is able to move. You got that motive, this one. But that petrol will also, the energy that you have put inside will get converted to so many other forms of energy. For example, your car is heated, engine is heated. Where did that energy come? From the input petrol. Correct? So now that is not useful power. So we are going to measure what is the output, useful output power divided by total input power. See, energy is conserved always. At least in this case, energy is conserved, no? So, but here we are not interested in all that energy that comes out. We are interested in useful output power. So, how much useful output power I am getting for the given input power? That becomes a figure of merit. That is efficiency. Correct? Now, okay. Students, I know it will be for some students you are finding it difficult and all. You are making your life difficult by keeping quiet in the class. If you are active and chulbuli, you aram se can learn science. Okay, you are frightened of the future. You are frightened of the exam. That is why you are making yourself life miserable. Don't be afraid of examinations and all. Examinations come, examinations go. You will all see. You be sincere and honest. God will show you the way. Don't worry. Don't worry. This is my experience. I have been teaching from 30 years, and I was a student once upon a time. So I have seen my friends, me, my brothers, sisters, everybody, how they were and what they are. Everybody will have a good chance. You be sincere and honest, be hardworking, God will show you the way. Trust me. Right now, without bothering about all that, you just say, I will learn nicely. If you learn nicely, you can do good work. If you do good work, then you will have very good life. If you don't learn properly now, then you cannot do work properly in the future and you will not have good life. It is not the college that gives you good life. It is the knowledge that you have gained will give you your good life. Your manners, your character, all those things matter. Now here, you see, here, what was your question, Mr. Adil? No, there was some disturbance. Once again ask.
Input power only I consider.
Output power.
Output power. So over there, like, so I don't consider why I disagree.
Then what do you want to consider? What are you interested in? Why are you using a rectifier? You are using a rectifier because you want DC, no?
Yes, sir.
That is your useful power, no?
But that is not purely DC, no, sir.
Okay, that is why I'm not considering other energies there. See, what is the useful output power? Useful output power. What is the useful output power? Once again. See, from a rectifier, see now this is input, this is rectifier, correct? This is rectifier. Okay. So you are feeding here what? AC power. Correct? What do you want here? You want a DC power. Correct? That is what you want. But what are you getting at the output? You are getting DC power plus you are getting AC power. Correct? And you can define efficiency. This is the useful power. So you are going to talk about DC power divided by input AC power. This is what is.
Resistance, sir.
No, listen. Don't. Did you understand this? Did you understand this? You tell me frankly, did you understand this? Did you understand this? I will make you to understand that. You tell me, did you understand this equation what I have written?
DC output is, sir.
Leave it. I will make you to understand. I understood your question. I will convince you. Don't worry. Now, we aram se try to understand. Aram se try to understand. Okay? Now, what is this waveform? This is VE. Got it? This is VE. And what is the current that will flow from the, see, now this is the diode and you are giving VE. Correct? So this is VE. Now, what is the waveform of the current that is flowing here? Waveform of the current that, see, now this is VE. What will be this? This will be V out. Correct? Okay. Now, what will be I out or IL? This is IL. What will be the waveform of IL? Waveform of IL will be what? V naught by RL. Correct? So it is V naught divided by RL. RL is only a scalar quantity. So the current waveform will also be like this. Agreed? This is IL. Okay, done. Very good. Now, what is the output power waveform? This into this. Hello? Correct? No? Understand one by one. One by one you understand. Now, here, I am going to write this waveform into two components. One is what? One is the DC component and one is the AC component. You remember? I have already told you. What is this? This is, one is the DC component plus the AC component. How will be the AC component? The AC component will be like this. Got it? This is it. Now I am interested in this. I am interested in that. Okay, I am interested in that. Okay. So therefore, the output power corresponding to this. What will be the output power corresponding to this? That will be IDC square into R. Got it? Okay. Now you see, this is output. So what is this? This line I have drawn. This line I have drawn is VDC. Hello.
Yes, sir.
Then this line that I have drawn corresponds. What is this line? This line corresponds to IDC. VDC divided by RL. IDC.
Yes.
Okay? So now IDC square into RL. What is this IDC square into RL? This is what? Useful output power. Got it? Got it?
Why that is only useful?
That is what is efficiency, man. See, first of all, I asked you what is the efficiency of a machine? Useful output power. This is the only useful output power. Of course, the total output power will be IDC RL square plus IAC RL square. IAC square RL. DC plus AC. But this one I am not interested. I am only interested in the DC component of the output. I am defining efficiency like that.
Okay, please.
See,
Yes, sir.
that's why I asked you, see what is happening to you, I'll tell you. When I ask you what is the efficiency of a machine, you just told the answer, sir, output useful power upon input. हाँ, मैंने बोल दिया sir, अभी teach करो. मैंने क्यों पूछा आपको वो? Why did I ask you that question? Because the concept of efficiency of a machine is what is that useful power you are getting for the total input power that you are getting. Understood? Same way here, the function of a rectifier is to convert the AC into DC. All the AC will not be converted to DC. Only a portion of the input power will be converted to DC. Just like how in a machine, a portion of the input power will be converted to output power. Correct?
Yes.
But the total output power is equal to total input power. The total output power will contain so many things. I gave you the example of car. The car moves. The car is also heated. What will you do with that heat? The engine is heated. It is waste. So like that for us in the rectifier, the AC power at the output is a waste for us. It's not going to do us anything because I am interested in the DC power. So I am writing the output as IDC square RL divided by the input. What will be the input? Input will be IRMS. IRMS. What will be the IRMS of the input? You see, what will be the IRMS of the input? What is this signal? That is VO. Hello. That means current will flow through the, see, if you connect a voltage source here, current will flow here. Input current will flow only when the diode is on. The current will not flow when the diode is off. Got it?
Yes, sir.
So IRMS is this Vin divided by RL. That will give you IRMS. So IRMS square, and this current is flowing through the diode and also through the load. So this is IDC square RL upon IRMS square RF plus RL. That is precisely what.
IRMS which you have considered, sir. That is for the input current.
अरे यार इनपुट करेक्ट सी ये जो करंट इधर से निकलता है वही करंट इधर भी फ्लो करता है ना करंट विल फ्लो ओनली व्हेन द डायोड इज ऑन व्हेन द डायोड इज ऑफ द करंट विल नॉट फ्लो so the waveform of the input current and the waveform of the output voltage will be same.
Yes, sir.
That is what I have written.
Sir, here, sir, which RMS are you considering? Which curves RMS are you considering?
This one, this IRMS. This IRMS you are seeing?
Yes, sir.
This IRMS only I told here. Yeah. See, what is this waveform? I wrote this waveform as what? VO, no?
Sir, but what we are supplying is something different, but it is using something else that is not of our material.
You are not following me, man. You are thinking ahead of me. What can I do? Tell me. When I was teaching, when I am telling this, what are you doing? See, now, this is the input waveform, agreed?
Yes, sir.
This is the output waveform, agreed?
Yes.
This input waveform is same as this output waveform, agreed? This part. This part of the input waveform is same as this format of the output waveform, agreed?
Yes, sir.
जो वोल्टेज इधर है वही वोल्टेज इधर है, agreed?
Yes, sir. That's not.
And whatever current is flowing through the source, the same current is flowing through the load, agreed?
Yes, sir.
So, and if you say this current is IN, and if you say this current is IL, is IN not equal to IL?
Yes, sir.
So therefore, the waveform of the input current and the waveform of the output current will be same. This is correct waveform. See, I have written here IL. What is this? Output current waveform. This is same as input current waveform, no?
Yes.
So RMS value of the input current is the RMS value of this signal. Correct now?
Correct, sir.
That is what it is RMS value.
Understood.
Good. दोनों को जंग लगना पड़ता है. ठीक है, समझ आया सभी सब लोगों को? देखो ये आराम से समझ लें. Okay, fine. So this is efficiency of the rectifier. Now you see here. Now efficiency of a rectifier. See here, efficiency of a rectifier. Now what did we write here? IDC square into RL divided by IRMS square into RF plus RL. Correct?
Yes, sir.
Now what is IDC square? IDC square is VDC square by R into VDC square by RL square into RL. Got it? What is IRMS square? V input RMS square divided by RF plus RL square into RF plus RL. Correct? Now, what is VDC square for half wave rectifier? It is V0 by pi. इसका square. And one RL and one RL will go, so you will be left with one RL in the numerator. What is input? What is V in RMS square? V in RMS square is V0 by, see here, V in RMS square. Hello?
Yes.
What?
Can't
Pardon?
we can't consider V in RMS.
I'll explain. So V in RMS means you should only consider the half part of it.
Okay, yes.
Then only it will become IRMS. Got it? Got it now? So V in RMS will be what? V0 by 2 square.
Correct.
Okay? For this one will go. So this will be left with RF plus R. Okay. So here V0 square will go, and you will be left with the what? Here you see 2 square will go up. So 4 divided by pi square. Divided by, if you pull this RL down, you will get 1 plus RL by RL. This 4 by pi square, what will you get? Calculate it, tell. Will you not get 0.406? Pi square is approximately 3 point something. No, 3 3s are 9. 9 is approximately equal to 10. So 4 divided by approximately 10, it will be 0.4 now.
Yes, sir. Correct.
So you will get efficiency as 0.406 divided by 1 plus R plus R. Got it?
Yes.
This is for half wave. So for full wave, what happens? This DC becomes what? 2V0 by pi square. 2V0 by pi. Correct now? So 2V0.
Yes.
So 2V0. So this will be twice.
Yes.
Got it? And this will also be, see here, this will also be twice. So if you take that, then you will get 0.180. Okay, so what I am trying to tell you is efficiency of half wave is this, efficiency of full wave is this. Right? Now, if RF RL is very less than N, then the efficiency of half wave rectifier is only 40%. Efficiency of full wave rectifier is 81.2%. Okay, now did you get these numbers correctly?
So that IRMS here in full wave will change, sir.
See, the output waveform will be like this, no?
Yes, sir.
That means the current will flow from the input for both the cycles. The current will flow for both the cycles, no? see for full wave, listen here, for full wave, V output DC will be what? 2 V naught by pi, agreed?
Yes, sir.
V in RMS. So V in RMS, see, now here the input voltage is like this. Now here you see, the diode will conduct for this portion also and for this portion also, for full wave rectifier.
Yes, sir.
Got it now?
Yes, sir.
So therefore, the current will be what? V in RMS divided by RF plus RL. Correct now? So this V in RMS value will, and whether you take waveform like this or whether you take waveform like this, the RMS value of this and RMS value of this is same. Correct?
Yes, sir.
So this becomes what? V naught by root.
Root 2, no, sir.
Root. I wrote here. Sorry, I wrote here. Sorry, I should read root. Oh, okay, you do it. So what happens here? Here in this equation, it becomes, see here it is 4, no? So this becomes into 4. Right? And here in the denominator it was 2 square, no? This 2 square went up and become 4. Hello?
Yes, that becomes 2.
This becomes 2. So that's why you are getting it double. Of course.
Yes, sir. Correct.
Got it. Okay, got it? Now, did you understand these figures? Hello, everybody. See, your learning must get completed in my class only. You will not have time to go back and learn and study and learn. There is no time now. You see now, it's already November, right? So complete your learning now. Concentrate and learn. Did you understand? Did you get this number? Both of you, everybody here in the class?
Yes, sir.
Now, what do you mean by efficiencies? What do you mean by efficiency is 40.6? What do you mean? And what do you mean the efficiency is 81.2? What do you mean by those numbers?
Sir, it means that only that much percent of the input AC current is converted to.
So, only 40% of the input power, only 40% of the input AC power is converted into DC power. And for full wave, 81% of the input power is converted to DC power. Got it?
Yes, sir.
Why don't you say yes quickly? You know my pause. So this is one. Now, this is, now see here. This we are writing if RF by RL is very, very less than 1. Okay? Now be careful here. If RF is equal to RL, you know, maximum power transfer theorem. I hope you have learned about it. When you have a source, the output resistance is equal to the input resistance or the source resistance, then maximum power is transferred. But here what happens here, only 50% energy will be transferred. Remaining 50% will be dissipated in the circuit itself. So here, if RF is equal to RL, then the efficiency is only 20%. And here, it will again become 50% of that, it is 40.6. Okay? And this RF value, in the bridge rectifier, the current will flow through 2 diodes at a time. So this RF value, you take it as 2R. Got it?
Yes.
Somebody's mic is mute. Please mute your mic. Hello? Somebody's mic is making noise. So in bridge rectifier, RF value you have to take it 2 times that of the resistance of PGDBA. In forward bias. In reverse bias, it will be infinite. Okay. I hope I made all these points clear, right?
Yes, sir.
Yes.
Okay. Now, quick ready recognition. See, I have made precise notes so that I can teach all these things fatafat. For full wave rectifier, the input waveform is having, say, supposing 50 Hz, the output will also have 50 Hz. For full wave, input is 50 Hz, the ripple frequency will be 100 Hz. And here you see, sometimes the name used is pulsating DC.
So then this word pulse will be used. That's it. Okay, the frequencies will be what? Now, quick comparison between the rectifiers. Now, half wave, center tap, bridge. Transformer necessary? No. Center tap. For center tap rectifier, full wave rectifier, you need a transformer. Peak secondary voltage will be peak secondary voltage. I suppose you understood. That is V out. V in maximum. Peak secondary voltage will be Vs, Vs, Vs. Peak inverse voltage for half wave rectifier. Whatever is the voltage, I have explained this to you. Peak inverse voltage will be same, but for center tap it will be double. But for bridge again it will be Vf. I think I have already explained this to all of you. Hello? Hello?
Yes, sir.
Peak load currents will be VL divided with this by this. Here will be 2 RD for bridge, 2 resistors, 2 diodes will be conducting at a time. RMS value will be Im by 2, Im by root 2 for this, Im by root 2 for this. VDC is this. Ripple factor 1.21, if you put the values. Ripple factor IRMS by root of IRMS square divided by IDC square minus 1. If you put this values, you get 1.21 for half wave. For center tap, it is 4.0.42. See, this is the figure of merit. 1.21 means, see, if the DC value is something, the ripple is 1.2 times higher than the DC value. And here, the ripple is less, 0.482 of the DC value. Efficiency just now we discussed. Ripple frequency we just now discussed. Okay, so this completes the study of the rectifiers in detail. Your questions will be on all these performance parameters. Shall I proceed? Hello?
Yeah. Yes.
One or two problems. Shall we solve some numericals today or tomorrow shall we solve? Are you still fine? Let me continue or shall we stop today? Come on. Okay, so today I'll end the class. We'll solve the numericals tomorrow. Just go through all this theory. Aram se, come fresh. We'll solve these numericals and be happy. Right? Done.